Hello, and welcome to this video lecture on demystifying simulations, part of your course on systems thinking and sustainability. Today's video lecture has three parts. In the first part, we talk about why we simulate and the sort of inferences one can hope to draw from simulations. Next, we'll talk a little bit about the different kinds of simulations we have out there and why one might use one versus another. And then the third part, and in fact most of this video, we will engage in a simulation exercise ourselves. We will do some simulating. And this part is actually itself comprised of two parts. The first is a modeling exercise, a mapping exercise. This will build on some of the work you've done earlier in the semester with stock and flow modeling. And then in the latter half, we will take the stock and flow model and simulate a pattern based on that model using a computer program that we write ourselves. And today we will take advantage of some of the latest technologies that we have that make simulating fairly accessible. In fact, it has never been more easy to write our own simulation. And so hopefully that part of the video will be useful for you as well. So let's get straight into it. Why simulate? Why do we engage in the activity of simulation? Well, I think it has to do with the world, which we often think of as occurring in the form of phenomena, and our knowledge of these phenomena of the world. And I will explain what I mean based on an example that I think we may all be somewhat familiar with, and that is the phenomenon of climate change. Now, for the most part, most of us, we know about phenomena based on observing patterns, which is to say, this phenomenon of climate change is often known to us based on various patterns. Like, so for example, increasing air surface temperatures all around the world over time, or shrinking polar ice caps over time, right? So these are patterns that we think of when we think about climate change, right? And patterns are typically something that is measurable, something that changes over time. You earlier in your semester, you've seen your behavior over time graphs. This is a classic pattern over time, right? And most of the time, these patterns are produced by one or more processes. So these are complex mechanisms, many different things that happen to produce these patterns, and these things, the sequence of the things might matter, or where and when they happen might matter, or how they are interdependent might matter. And so these are the processes that generate the patterns that we can see, and very often the processes themselves are fairly hard to see themselves, right? So what we can actually see, what we can actually observe, are the patterns, right? And so I said the word observe because that is what sits between the process and the pattern, which is the act of observation, right? At the most basic level, we observe with our eyes. We could, for example, go on hikes to the same mountainous spot year after year and see the snow line is receding at the same time of the year. That could be a pattern that we associate with climate change. We could also use instruments like a thermometer that shows that the temperature is increasing over time, or satellite images to talk about the polar ice cap. So there's many ways in which we can observe patterns, and often that includes that involves instruments of some sort, right? And so from this pattern comes our knowledge of the pattern that you can think of as a pattern model, right? You've heard earlier in this semester about mental models. You can think of a pattern model as a mental model that associates one pattern with another, right? So think of this pattern of increasing air surface temperatures over time, right? So if one were to sort of go and measure, and people have done this, measure air surface temperatures over the last century, one would find that those temperatures are increasing, right? At the same time, if one were to measure the human population, the whole world, or at similar time points, one will also see that the human population is increasing, right? So here we have a pattern model where the increase in human population is associated with increasing air surface temperatures or decreasing polar ice caps. Now note that these are just two patterns that we associate with each other. They're correlated, we're not necessarily saying that we know how increasing the number of humans increases the air surface temperature, right? So this is the essence of a pattern. It's just associating two patterns with each other. Some of you may have taken statistics in the last couple of years, and so you may be familiar with a very, very common pattern model, which is a linear regression model, right? Where you are predicting some kind of outcome based on some predictor variable, right? Again, we don't necessarily say that we know what the mechanism here is, but the association is robust and we're confident in it. And so that is an example of a pattern model that can be very useful and is put to use every day without necessarily knowing the mechanisms there, right? Next comes our observation model. Now, often observation models aren't a formal mental model, simply an acknowledgement that how we observe patterns might have an effect on the patterns that we observe, right? Which is to say that the thermometers that capture the air surface temperatures over here in North America might be different in some way from those that capture the air surface temperatures in, let's say, Australia, right? So there could be differences in the instruments themselves. There could be differences in the practices of the researchers, what time of the day they collect the temperature, do they round up, do they round down? So there are all these different effects of the act of observation on the resulting pattern, right? And sometimes you will see these observation models included in the pattern model in the form of control variables, right? So that's a kind of a very explicit use of an observation model. Sometimes it works differently, right? But that's the idea, right? That you are accounting for the fact that the way you observe the data may have an impact on the data itself, right? And then from the observation model, we have the process model, right? So this sort of sits on top of the observation model and the pattern model. And the process model is, in some ways, some understanding of the underlying process that generated the pattern, right? And so remember we said that the pattern of increasing human population is affiliated or associated with a pattern of increasing air surface temperatures, right? So if you think of this as a CLD, you have sort of one node and there's an arrow and goes to the other. Now, what if you had a number of different steps between these nodes, right? What if you had increasing, human population leads to increasing, consumption, which leads to increasing food and industrial production, which leads to increasing greenhouse gases and therefore increasing air surface temperatures. Or increasing human population leads to the increased need for land to live in, and which leads to increased deforestation, which leads to reduced carbon capture, which leads to increased air surface temperatures, right? So these are sort of, many steps in the middle, and this starts looking more like a mechanism, right? Because you have all these different things that happen. Sometimes the sequence of things might matter, but importantly, these things aren't always linear sequences of events, right? So process models aren't necessarily always this chain of events. Sometimes they could be loops. Sometimes they could be sort of more complexity, right? And when this happens, it's sometimes very hard to know or guess at what the resulting pattern might be based on this kind of process model, right? So that's sort of where we start trying to do computer simulations, where we will sort of build in the logic of the process model into a computer simulation and kind of see what that logic produces in terms of a pattern. And if that pattern produced by this simulation based on our process model looks anything like the pattern produced in the real world, right, by the real process, then one can infer that our process model is something like the process that generated the pattern in real life, right? So that, in a way, simulation can be a way in which we validate the process model by generating a pattern based on the process model by simulating a pattern. And if that pattern looks a lot like the pattern produced naturally by the real world process, then that tells us something about our process model, right? And so validation is an important thing, important aspect of simulation, validation of process models. And once we have validated and we have confidence in our process model, what we can then do is say, okay, what if something was different, right? What if we had taken some steps, to intervene in the ongoing process? What if we had corrected some mistakes? What would happen then, right? So this what if scenario, playing out these what if scenarios, is another important and powerful use of simulations, right? And so today we'll do a little bit of that validation, but then we'll do quite a bit of the what if scenario exploration using the simulation that we create today. All right. So this is sort of our at a very high kind of level why we simulate, right? Which leads me to types of simulations, right? Because you can simulate in a variety of ways to achieve a number of different goals. So the first way to start thinking about these different types of simulations is, how is the simulation being done? Because simulations can be physical, right? You can have people and real buildings, and you're doing something real, and it's a rehearsal in some ways. And a fire drill is a very good example of this, right? Where you may have some process model in your head about how the orderly evacuation of a building under conditions of fire might happen. And so you do a fire drill, you simulate that event, and you may find out that actually there's a choke point in this one stairwell, or there's this blind spot in this other stair and on this other floor, right? And so that's physical simulations to then explore the scenario of, in this case, a orderly exit from a building under conditions of fire, right? Now, sometimes you may not have the option to physically simulate something, right? So you've been working with En-ROADS. Now, I would think it'd be impossible. I can't imagine a way in which we could simulate the effects of electrification on the air surface temperatures over time, right? That would be very, very hard to physically simulate that, right? So in those cases, computer simulations are essential, and often computer simulations will synthesize and bring together insights from many, many different studies and sort of combine them in a very powerful way, like you're seeing in En-ROADS, right? So in these cases, often physical simulations are not possible, are not practical, and so computer simulations are a very, very good alternative. Another way of thinking about simulations is based on who is doing the simulating, right? And so you could have sort of a simulation that is built by a small group of experts in order to maybe test out something or create a product really quickly. And so a really good example could be the Moderna vaccine, right, which is one of the COVID vaccines. And some of you might be familiar with the story of this vaccine, where a lot of the development of the vaccine was done using a simulated environment where they simulated human cells and what the vaccine might do and how it might generate an immune response, and that allowed them to make the vaccine very quickly, right? And so this is a simulation done by experts who probably understand the inner workings of the simulation fairly well. They want to sort of see what the pattern is played out, right? And this is in opposition or in contrast to what I might call a public-facing simulation, where often these are simulations where the people who are using the simulation did not build the simulation themselves, and often they don't have a very, very detailed understanding of the inner workings of the simulation. And so En-ROADS is a very good example of that. You could also have sort of maybe simulations built for a corporation to test out some kind of marketing plan. I've actually built one of these simulations. And so these are simulations that are done and used by people who didn't build the simulation, who don't understand its inner workings necessarily, but they don't need to, right? So if you're a policymaker, you don't necessarily need to have a very, very detailed understanding of the climate science, but you should be able to speak to what will happen if we do this or that, right? And so public-facing simulations like En-ROADS can be very powerful and very useful as a way of persuading people to do something, right? So that's an important way of thinking about simulations. Another way of thinking about simulations is sort of when the input information is sort of inserted into the simulation. So you could have something like an automatic simulation, which is, I would say, a good number of these simulations where what we are doing, the humans, we're mostly setting up the initial conditions, right? And then it kind of plays out for a predetermined period of time, and it tells you the result. And so this is exactly what you do with En-ROADS. We sort of do these sliders, and it says what's going to happen over the next 100 years or so, right? And this is in opposition or in contrast to an interactive simulation, like a flight simulator, where you are actually putting in inputs all along the way, right? And so these could have different reasons. Automatic simulations are more about these long period of time that you're trying to simulate really quickly, and interactive simulations might be trying to simulate something that is more in real time, for example. Okay, another way to think about simulations is based on whether or not they're random. So En-ROADS is a deterministic simulation, which is to say that if two of you from this class were to independently put in the exact same starting conditions in En-ROADS, it's highly likely that you'll both get the exact same output, right? The same result. And that's because for any given set of initial conditions, if you always get the same result, that's a deterministic simulation, versus a stochastic simulation, which is often based on some kind of probability of something happening, where even with the same starting conditions, you might get a number of different outcomes, and this could be very useful. especially when you're trying to sort of predict the likelihood of something happening. And so a weather prediction model is a very good example of one of these stochastic simulations, right? Because you'll rarely ever hear a meteorologist say, it is going to rain tonight. They'll say, oh, there's some percentage of rain today. And so randomness is often important. And often, if you have a model that is deterministic and it doesn't play out that way, public might lose trust. So sometimes randomness might even be a way of getting people to sort of accept the kind of the outputs of the simulations in some ways. Um, and then there's sort of simulations based on how they treat time and categories. And so you could think of simulations that treat time as this thing. So you going from one unit of time to another, or from one category to another, and then you have simulations that are more continuous. And the distinction is not super important, except in the sense that the mathematics of these two kinds of simulations are quite different, right? Discrete time simulations have fairly simple mathematics, and in fact, what we're going to do today is a discrete time simulation, which you will be relieved to know does not have any advanced mathematics or calculus, which is true of a continuous time simulation, which does require some calculus. And there are advantages to doing the continuous simulations. They are much more complicated, but there are important aspects of the simulation, important measures, important values in the simulation system that you can derive without having to actually run the simulation. You can just do it through the mathematics, and that could be very important, especially in the context of healthcare simulations, where you want to know sort of how much you want to flatten the curve, or you might have heard that term. And so there are things that you can do with these continuous type simulations based on the math itself. In fact, all the COVID-19 simulations that were built during the pandemic by the government of Canada were continuous time simulations, and you can sort of go and click on that link over there and take a look at them, because what we're going to be doing today in our simulating exercise is build another COVID model, but this one's going to be a discrete time model, right? And so yeah, this brings us to our the third part of this video, and so I think this is the rest of this video, is the actual exercise of simulation, right? And so what we're going to be doing today is we're going to be simulating COVID-19, and I'll get to what that means more precisely in a minute. But before we move on, I want to give you two options of how to continue. Option one is you just continue watching this video and you watch what I do. Both the mapping exercise, the modeling exercise, as well as the programming exercise. Option two is that you do it along with me, right? And what I'm going to do is I'm going to sort of build in pauses and breaks for the rest of this video. So it's going to give you the chance to pause and do things on your end. I will also provide some resources to do some of that programming along with me, right? Again, I don't think either option is better than the other. I think both are perfectly fine. You can even do both. You can do one and do the other one later. It is entirely up to you. I think both can be very useful. But should you choose to do option two, I'm going to require you to collect two important technologies. The first is a pen. It's a very important part of simulating, because a very important part of simulating is writing out that process model, right? Building the process model is a very important part of the simulation, especially in this day and age where once you have the model mapped out, writing the computer program is going to be fairly relatively straightforward. And today, where all you're going to need to do that programming part is a browser, because we're going to be using a cloud-based programming environment where I have written most of the code for you, but if you want to code along with me, you can sort of modify the code and run it with me. But again, you don't need to actually install anything on your computer. You just need a browser. I will tell you, I'll show you the link of how to get to the work environment when we get to that point. But for now, all we need is a pen, or just continue watching this video. Okay? All right. So, simulating COVID-19. What do we mean by that? What are we actually simulating when we say we are simulating COVID-19? Well, the first thing to start thinking about is, why are we simulating COVID-19? And to answer that question, we need to sort of ask who we are, right? What is the persona of the person who's doing the simulation, or who has commissioned the simulation? And today we're going to be using the persona of a public health person, right? Someone who is in charge of a public health system. Let's say someone in the Ministry of Health, at Ministère de Santé à Québec. And this is important because who the person is will influence the kind of stocks we're interested in, right? Remember, stocks are things that can be counted or measured, and things that change over time. And so if you are, for example, someone who's in charge of producing masks, the stock you might be interested in is the number of stock of masks consumed, because you might want to know how many masks to produce over time, right? If you are, for example, in charge of a hospital, if you're a hospital administrator, you might be interested in knowing how many nurses you need to have on staff at any given point along the pandemic, right? So you might be interested in staff as a stock, right? But today we're going to be doing a public health official, right? So I'm going to give you a few seconds if you want. You can sort of take a piece of pen and paper and write down some ideas of what might be some stocks that are that a public health official might be interested in simulating, interested in counting and measuring and seeing the pattern over time. I'm going to give you some a few seconds. Did anyone come up with people? Right? There are many different stocks that a public health official might be interested in. They might be interested in beds, hospital beds. They may be interested in supplies and vaccines. But I think a really good thing that a lot of public health people might be interested in, as in terms of stocks, is people, right? Because they are interested in managing the health of a population of people, right? And in the context of a infectious disease, right, in a pandemic, one might be interested in counting or measuring or counting or looking at the change in time in the number of people who have COVID, right? So that, I think, that's a very important category of people, as people who have COVID, right? In the context of a pandemic. Now, what other categories of people might be important to someone, to a public health official? Can you think? Did anyone think of people who don't have COVID, right? So if you're thinking of a population, you have population of people who don't have COVID and people who have COVID. Now, importantly, because this is a disease that is infectious and that can confer some kind of immunity, we might be interested in distinguishing people who don't have COVID yet, right? In the sense that they are not immune, they are susceptible to the disease, and distinguishing them from people who don't have COVID anymore, right? So these are people who had COVID and who have since recovered, right? So they are no longer in that same pool of people who are very likely to get the disease. You may also be interested in people who got vaccinated, right? Again, this is a category of people who have been taken out of this category of people who don't have COVID yet, right? Because of the vaccine. So these are, I think, the important stocks in this simulation that we want to think about. I am going to be using some general terms for these because I don't want to keep saying people who don't have COVID yet and people who don't have COVID anymore. We're going to use some standard terms from similar models that have been deployed and were deployed during COVID: infected, susceptible, recovered, and vaccinated. Now, oftentimes you will hear models that are like the model we're going to build today referred to as SIR models, and when they're referred to as SIR models, they're referring to susceptibles, infected, recovered, right? So that's an important type of model. You might also hear these models referred to as compartmental models, and these are, in this case, compartment refers to each of these stocks. Okay, so now that we have our major stocks in place, let's start thinking about flows, right? So if you may remember, flows are ways in which you can increase or decrease a particular stock, right? So let's start with our first stock, which is infected individuals. Specifically, let's start talking about infected unvaccinated individuals, right? Because now it'll start mattering whether we're talking about vaccinated or unvaccinated individuals for a variety of reasons. And so our first talk is infected unvaccinated people. I'll give you a second. Can you start thinking and writing down some possible ways in which you can increase the number of infected individuals, right? And start thinking about those other stocks, right? So how can people from any of those stocks come into this particular category, right? What are the inflows into infected? Well, I think the most common inflow, the most sort of maybe not obvious, but a sort of a major inflow is that someone who is susceptible to COVID gets infected and is now infected with COVID, right? So a susceptible person comes into the infected stock, right? So this is an inflow. Can anyone think of any outflows? Well, I think a sort of a pretty important one here would be that an infected individual recovers from COVID, right? And then we have the other way in which someone is removed from the infected category, which is that they die, right? And because COVID is unfortunately one of those diseases that is associated with a significant mortality rate, higher than comparable viral diseases like influenza, right? So mortality is an important outflow for infected individuals infected with COVID. Okay, and so next we have infected vaccinated, and you'll notice that inflow 4 looks a lot like inflow 1, and outflows 5 and 6 look a lot like outflows 2 and 3, right? So these are very similar in terms of the direction, right? However, the rates might be very different. Now, this is where we start talking about flows versus rates. Now, a lot of times when you do stock and flow modeling, we tend to use flows and rates somewhat interchangeably, because these flows often have sort of a directionality and a magnitude. But when we start talking about simulation, it is important to sort of think about these concepts slightly distinctly, because one of the big things that we do with simulation is the what if scenario modeling. And one of the big ways in which we do the what if scenarios is by modifying rates, by increasing or decreasing rates. And in fact, we very rarely change the direction of flows in the course of what if scenario modeling using simulations, right? So what we're really manipulating is rates. And so it is important to start thinking about rates and flows as slightly different concepts when we come to simulations, right? So it's not, I think it's okay to think about them interchangeably when you're just doing stock and flows. But when you're doing stock and flows for simulating, start thinking, at least in your head, of these things as slightly different. Our next stock is the susceptible bucket. So these are people who can get COVID. Let's give you a few seconds and let's talk about some inflows into susceptibles. Okay? Well, the most common ways in which you can get into susceptibles is losing immunity, right? So people who have got COVID, have recovered from COVID, had immunity, they lose the immunity, they're back in the susceptible bucket. Or you got vaccinated, and then again you lost your immunity over time, and you're back in the susceptible bucket. Now, some of you might have included births in here, so that's another way in which you could enter into this category. You might just be born, and that is a perfectly good inflow. But for the purposes of today's exercise, what I'm going to say is we're talking about a short enough timeline where natural births and deaths can be ignored. Obviously, they are happening, but I think in the timescales that we're going to be simulating today, it maybe does not make a big difference. And so we are not going to include births and natural deaths in this model. But of course, we will allow for disease-related deaths or excess mortality, as you may have heard of in the newspapers or anything like that. Okay, and some outflows for susceptibles. You have susceptibles getting infected. You notice that this is actually the same flow as the one we saw over here, right? So this is an outflow for susceptible, but it's an inflow for stocks. Now this will become important in a few minutes here, the fact that an outflow for one stock is an inflow for the other. But let's keep going on with this exercise. So vaccinated, you get taken out of the susceptible category if you're vaccinated. Let's go to our next stock, recovered individuals. I'll give you a second. Okay, these are the major flows for recovereds. Okay, and then we'll go to our last stock, which is vaccinated individuals. And so now we start seeing that we have obviously people getting vaccinated, and you could have gotten vaccinations even if you've had the disease before, or you could have gotten the vaccination, got infected. Remember, some of you might remember that these vaccines were not perfect. You could still get infected even if you had the vaccine, but there are other benefits of the vaccine that we'll talk about in a second. But even those infected, vaccinated individuals do recover, and then they come back into the vaccinated category. And then you have the outflows for vaccinated. Okay, so those are our major flows. Now, let's balance them out. Remember I said that this inflow is the same as this outflow? Well, this is important because when you are doing simulations, you're basically moving individuals from one stock to another, right? And if an outflow from one stock doesn't actually go into an inflow to the other, then those individuals are lost from the system. And we need to be a little careful about when and why we allow individuals to leave the system, right? So let's try to do this balancing exercise. So like I said, 1 and 9 are actually the same, so they get balanced. Let's see if we can balance number 4, vaccinated, gets infected. That looks a lot like 17, right? And so let's go down this list. We're gonna one by one, we're gonna make sure that we're balancing out all the inflows with the outflows, right? Recovered gets vaccinated, infected, vaccinated, recovers. And you will notice that we are left with 2 outflows that do not have a counter inflow, right? And these are the 2 mortality outflows, right? And sometimes these might be referred to as a removal rate, but this is basically these are both flows that leave the system, but that's okay because we have this is the sort of this is the death that we do allow for in our assumptions, right? So I'm going to mark them in a different color, but they're outflows nonetheless. Okay, so now that we have our balanced flows, let us begin to draw out the model. All right, and again, you can do this with a pen and paper, or you can do it with PowerPoint if you wish. There are many ways to do stock and flow models. Some of you might be familiar with Vensim. That's another kind of interesting and very user-friendly way to do stock and flow modeling. So now let's start drawing this, right? So the way I like to do it personally is I like to sort of take this stock and flow table and use that as a reference point. And the first thing I do is I put down the stocks on the paper, right? And so here I've put down the 2 infected stocks, which I am terming I sub V for infected vaccinated and I sub U for infected unvaccinated. I'm going to put a box around them because there's going to be some cases where it doesn't matter if you're talking about a vaccinated or unvaccinated individual, and some cases they do, so I'm just going to have this additional gray box around the 2 infected categories. Then we have our susceptibles, our recovered, and our vaccinated. Now the first thing I'm going to do is I'm going to take our 2 unbalanced outflows. I'm going to stick them in there, right? So these are our 2 mortalities. They are leaving the system, and so I'm going to add this little cloud. The convention in stock and flow modeling is when you see the cloud, it means that you are leaving the system. It could also mean that you're entering the system from outside. So if we had allowed for births in this model, you would see an arrow coming into the susceptibles with a cloud at its end, but that's not the case over here. So our 2 unbalanced outflows first. Now all the other inflows have a counterpart here, so we can actually just keep going down this column and ignore this outflow column for the rest of this drawing exercise, right? So let's start with the first inflow. So this is an inflow into infected unvaccinated, right? And it's from susceptible, okay? So that's our first inflow into infected unvaccinated. Okay, so the next one is an inflow into infected vaccinated, and it's from vaccinated, right? So that's our second inflow. Then we have an inflow into susceptible. There's 2 of them. One is coming from recovered and the other is coming from vaccinated, right? So there's 2 inflows into susceptible from recovered and vaccinated. And then we have recovered. We have an inflow coming in from infected unvaccinated. There we go. And then we have our vaccinated category with 3 inflows, 1 from susceptible, 1 from recovered, and 1 from infected, right? So susceptible, recovered, and infected. So this is our model. As you can see, it is certainly not a linear sequence of steps. and so the pattern that this model might produce in terms of the number of any of these stocks over time, I'm not sure it's very easy to intuit. Some of you might have the intuitive ability to know what that pattern might look like, but I personally find it quite challenging. So I'm glad that we have the simulation to try and tell us what this pattern is going to look like generated by this particular model. But before we can get to that, we need to start talking about rates, because these flows tell you the sort of the directionality, right? So from which stock to which stock you can have movement, but they don't tell you how quickly or how slowly that might happen, right? And so now we have to do rates. And again, this is a convention in stock and flow modeling. It's these hourglass looking icons. And so here are the rates, and we'll try and assign rates for each of these. Okay. And so the first rate is susceptible infection rate. And before I get into that, I want to tell you about this very important thing. All these rates are per some unit of time. Remember, this is a discrete time simulation, so we have a discrete unit of time. And that unit of time that we're going to do is a day. Again, so think about how we validate our simulation process models, is that we generate a pattern and then we compare it to a real pattern. Now, if you some of you might remember, but a lot of times the reportage around COVID was in terms of days and daily caseload, so number of deaths per day, number of new cases per day, It was often reported in the terms of days. So I think days are a pretty good unit of time to sort of do the simulation in, and it'll also generate a pattern that we can then sort of compare to something that we actually produced during COVID, right? And so this small I sub u is the susceptible infection rate per contact. So this is the rate at which susceptibles get infected based on their contacts with infected individuals, right? So it's important here to think about to sort of unpack that statement, right? So for a disease to spread in a population, you need susceptible individuals, and you also need infected individuals, and you need them to come in contact with each other. And so one of the assumptions that we sort of make in this model is that the more susceptibles and more infected there are, the more likely they are to come into contact with each other. Which is to say that everybody is equally likely to come into contact with everybody else, and so if there's more of one type of person, they're more likely to come in contact with another type of person. And so this is a fairly good assumption to make when we're talking about dense urban areas like cities with a lot of kind of apartments and dense housing and public transport and common spaces. It's a great assumption to make if you're talking about the spread of disease within a single dorm room, for example, because there certainly there's a lot of common areas and a lot of likelihood of contact. But even at the level of the city, this is typically a good assumption to make for a dense city because we assume that it is possible for everyone to come into contact with everyone else, either directly because they're physically coming into contact or because they come into contact with something in common, like a common space, or they're in the same subway tunnel, or they're touching the same railings in the public transport, and so on and so forth, right? So there's directly or indirectly, it's a decent assumption to make that everybody has the potential of spreading their virus to everybody else, right? And so that is an assumption that we make in this kind of model. It would not be a good assumption to make if we were trying to model the spread of the disease through a very sparsely populated rural area, for example, right? So that's not a good assumption to make there. But in the case of Montreal, I think a fairly decent assumption to make. And then we have the vaccinated infection rate. So the assumption here is that the individuals who are vaccinated, even if they come into contact with sick people, they get infected at a different rate from the susceptible individuals, right? Again, this comes down to the nature of the vaccine and what its mechanisms are. Not all vaccines prevent new infections. In fact, as we know, with the COVID vaccines, that was not necessarily the case. Another important sort of factor here is social distancing. Again, we're talking about contacts, so an important behavior that can modify contacts is social distancing. And so let's assume that we are able to convince some fraction of the population to practice social distancing. That'll, of course, change the contact rate of individuals in the system. Okay? And then we have our recovery rates. Again, so this is where we sort of start thinking about the vaccines kind of mode of action. We do know that, for example, that several of the COVID vaccines, they led to a much shorter disease duration, so your recovery rate is faster. They also caused a much less severe form of the disease, right? So the mortality rate is also less severe. So all of these things you can start thinking about in terms of vaccine efficacy. And in a more sophisticated model, you can sort of try to look at the impact of vaccines that might, for example, really reduce the mortality rate but not do anything to the infection rate, or maybe they really reduce the infection rate and they don't impact the mortality rate at all. But for simplicity's sake, we're going to assume there was just one vaccine in the system here, because we're not necessarily looking at modeling the impact of one kind of vaccine versus the other. And so that's the simplifying assumption we'll make, that there's just one vaccine here. And then there's the actual vaccination rate, right? The rate at which people will take the vaccine. And one can imagine that there might be some difference between people who have already got COVID and recovered from it and people who've never had COVID in terms of how willing they are to get their vaccines. Of course, that might not be up to them. You might have fairly strong mandates, and so then you might have a much more even vaccination rate among people who have and have not had COVID. And then finally, you have your immunity loss, right? We know that both natural immunity and immunity granted by the various vaccines is not permanent, right? Which is why you have to keep taking booster shots. And so there's some duration of immunity so that you get from these different methods. And so if you have some duration of immunity, 1 over that duration of immunity in days is the rate at which that immunity is lost. And so these are our important rates in our system. Okay, so we have our stocks, we have our flows that have both the directionality and the rates. Okay, and so this is our process model, right? At least as it has been mapped out. We have to do one more step before we can start simulating, and that is writing it out. And before we do that, I want to quickly recap our assumptions that we made. Like we said, first, this is a closed system, which is to say no births or no natural deaths, but excess mortality or COVID mortality is possible. We are talking about a perfectly mixed population. Everyone can come into contact with everybody else. We do say that we will assume that people who want to do social distancing are capable of doing it, right? We know that from real life that maybe not is not always the case. It wasn't always true. But let's assume here at least that if you have the intention and you want to social distance, you can in fact stay out of contact of other people. We'll also assume that there's only kind of you either have COVID and you recover or you die. There's no long COVID over here in this system. And we'll also assume that there's a constant death rate, which is to say that it doesn't matter how old you are or how crowded, how many other people have COVID, the death rate is still the same. Now, again, I don't know these are necessarily the best assumptions to make with COVID. We do know, for example, that the elderly were particularly susceptible to COVID, but we don't have any age structure in this model, so we'll assume that it's all the same. We also know that crowding affected mortality, especially early on in the pandemic. Some of you might remember when the disease hit Europe. It was really bad because all the hospitals got crowded very quickly, and there was a lot of excess mortality, excess death, not necessarily because people had the most severe form of the disease, but actually because they weren't able to get basic care in time, right? Basic respiratory care. So crowding can actually make the death rate much worse, right? But we'll assume that's not the case here today. Okay, so now let's get to the final step before we get to the computer program, which is essentially writing out the logic, right? Now we did the drawing, right? We mapped out the system in terms of the drawing. Now let's try to kind of speak out this system in a series of statements relating to each stock, right? And like I said, this is a discrete time simulation, and so what we're going to produce are these statements which correlate roughly to a mathematical statement in arithmetic, right? So it's a very simple mathematical statement with pluses and minuses, no calculus, right? So something that can be expressed both in English and in very, very simple mathematics, right? And why we need to be able to express this in English, I think, it's important both because it helps us understand what we're actually trying to simulate, and also we'll get to it once we come to the programming technology, where being able to say something out in English is actually going to be very useful to us. Okay, so let's start with a statement, a descriptive statement about how the number of infected unvaccinated individuals changes over time, right? We'll try to be as simple as possible, right? So this is our stock, infected unvaccinated individuals. Let's bring our flows here, just as a good way to remind us of what we're talking about. Okay, and so the number of infected unvaccinated individuals on day t, so I sub u at time t, right, is equal to that same number, so the number of infected unvaccinated individuals on the previous day, I sub u at t minus 1, right? So today is equal to the same number of individuals yesterday, number of infected individuals yesterday, plus the inflow, which is the number of susceptibles that get infected, which is the number of susceptibles in the previous day times the number of infected individuals, both unvaccinated and vaccinated, right? So this is the number of contacts between susceptible and infected individuals on the previous day, times the fraction that do not social distance. So this is the effect of contacts, right? Because if everyone was social distancing, there would be no contacts, times the infection rate per contact, right? So now we have sort of the contact rate times the infection rate per contact. So this is our inflow minus the outflows, right? So we have two outflows here, which is our two removals, right? So first is the number of infected unvaccinated individuals on the previous day, right? The same number from the previous day, times the mortality rate, times the mortality and the recovery rate, so the rate at which these individuals leave this system, right? And that gives us the statement over here, right? So these are, if you just sort of convert these English sentences into this math, you get this mathematical statement. You'll notice there's no fancy calculus. It's just addition, subtraction, multiplication. I believe not even any division, right? Wow. So super simple. I love it. And again, if you wanted to make a fancy model, you sort of and you are willing to dabble in calculus, all you have to actually do is sort of is differentiate these two sides with respect to time. So where time, instead of being 1 day, becomes infinitesimally small, and then voila, you get a calculus. You'll get a differential equation with respect to time, and that's a continuous time simulation, right? But we're not going to do that today. We have a simple statement which can be read in English or in in the language of mathematics, and this tells us about how the number of infected unvaccinated individuals changes over time, and you can make a similar statement for each of our for our stocks. I'm not going to do that here today. I'm not going to do that right here, but you'll see it when we get to the programming. Because now, let's get to the actual coding activity. Now, like I said, for those of you who want to code along, what I've done is I have created a workspace, an online programming workspace for each of you. So if you follow this path, you'll find a document with your names on it, and each name is associated with a link. Click on the link, and you will get to Google Colab, which is where we are going to do our coding. Okay, and so you click on the link, and you should get to something that looks like this. So this is a Colab notebook with the R programming language. So basically, Colab notebooks are web pages which have chunks of code, which you can then you can modify, and you can and then you can execute this code, and then somewhere in some server owned by Google, a computer spins up and it does the calculation, and then you'll see the results. And so this notebook has been written by me. I have written all the code for you. You don't have to really know how to program, but you can sort of read along. The stuff that you see in green is actually comments. It's describing what the programming code does. The stuff out here is more sort of telling me why I'm doing each part. And this notebook is divided into 3 chunks of code. One where I set the stocks, the second where I set the rates, and the third is where I establish the flows. You'll see those statements that I just described in the last slide over here. And basically, this is a computer program that basically takes the statement and operationalizes it for a number of different times, each time being a unit of time. So it just keeps recalculating the number again and again and again, and then we'll sort of look at what pattern is produced if this logic is played out for a number of days in sequence, right? And so this is our notebook. A couple of other features that I think are useful with Colab that I think you might find helpful. Well, the first is, of course, you don't actually have to run any of this. You can simply look at what I'm doing over here, and you'll be able to see kind of what this kind of program will do. But if you actually want to play along and you want to modify things beyond what I talk about today, you have a really useful AI assistant here, which is Google's assistant called Gemini. And you can do a number of things with Gemini. Like, for example, I can say, write me a discrete time SR model of COVID-19 in R, right? So this is what I've done over here. Let's see if Gemini can do something similar for me. Okay, so we have it has created a model. You can see it has now creating, initializing some parameters. It's showing population, some different rates. That's exactly what we've done over here. We have our population, we have some rates. It's setting up some initial vectors. That's what I've done. And then the actual simulation in the form of a loop, which is also what I've done. So you can see that you can actually ask Gemini to create a model for you, and it will do it. Now, of course, I have done a lot more of commenting because I'm hoping that you sort of read and you learn from this. But let's say you actually are unclear about what I'm doing over here. You can actually ask Gemini, explain chunk 1, right? And it'll try to explain what I'm doing over here to you. So you can say, oh, look, it's actually setting up the initial population size and the simulation duration and stocks for this model. So it can actually help you understand the code. It can also help you write your own code. And so I hope that this is something that you feel free to engage with. Like I said, each of you has your own kind of workspace. You can try and mess with it. You can do what I'm gonna do. You can do whatever else you want to do. You can use Gemini if you wish, and I do hope that you feel that that this is helpful. That helps you, especially if you're not very familiar with programming. Having something to converse with might be very useful. Okay, with all that said, let's get into the actual programming. This first chunk, as I said, was stocks. As you can see, I've sort of set the length of the simulation. I'm going to run it for 120 days. So that pattern that we talked about, right, which is based on what was in the previous day, what is the current day's infected, susceptible is going to look like. We're going to do that 120 times, right, and then we're going to see the pattern. I've set a population size of 100. I think it's just a nice round number. What you can also then do is it lets you kind of think of numbers as percentages or interchangeably. It's just a simple number. I like to use 100. It's good. It's easy to read. It's easy to infer things from it. The next I have basically the various stocks, and these are vectors. Vectors are basically sequences of numbers. Here I basically have the initial conditions and then a bunch of zeros, and we're going to fill in those zeros with simulated data. And so let me just run this code for you, and you'll see what I mean by that. Usually it takes a few seconds to run the first chunk as it connects to Google, and there you go. Right, so now you can see what this looks like, these initial conditions, right? So susceptibles, you start off with n minus 1 susceptibles, right? So this is 99 susceptibles, one infected, and then everything else is 0. And we'll fill in these zeros with simulated numbers as we run the simulation, right? And so we have these vectors for each of our stocks. Next, let's get to rates. And so really what we're going to be doing today is we're going to be messing with these rates a few times. You can see I've set up some initial conditions for us over here. Let me just tell you what the implicit assumptions here are. I'm saying here that the infection rate of the the vaccinated and the unvaccinated people is different. What we're trying to say is that if you're vaccinated, you might be slightly less likely to get the disease than if you were purely susceptible, and that might be true. Based on what we know of the vaccines, we'll also be able to manipulate the fraction of people doing social distancing. At least initially, we'll say that it's 0. We'll also know that the vaccine works in a few different ways. The recovery rate is better, the death rate is lower. So these are two different ways in which the vaccine is effective. And then we're going to assume that they have roughly the same immune loss for natural immunity and vaccinated immunity, about 6 months. And then we have the ability to manipulate the vaccination rates. Let's assume, at least initially, let's run it without any vaccination, right? So let's run these rates, and then we're going to run our flows. As I said, these are the different flows, one for each stock, and we're basically going to run it 120 times and see what pattern it produces. Okay, now we ran that, and there's some other stuff in here to plot this data. We'll see what that looks like. But here you go, right? You start off with 99 susceptible individuals. That number starts going down as people get infected. That infected number starts going up. There's no vaccinations in place in the model currently. And so here you can see the pattern, right? So let's talk about some of the things that you're seeing over here, right? You can see overall there's some mortality in the model under these conditions. The overall population size does decrease over time. You start off with everybody, almost everybody susceptible. That number decreases as the number of infected individuals increases. Of course, there's a spike. You run out of people to infect at some point, right? You're almost down to 0. And so then at that point you have the infected people also coming down as they recover, but there's just not enough new susceptibles to infect. So then you sort of end up at a kind of low level equilibrium where you slowly have people recovering and getting reinfected and whatnot, but it never completely goes away, right? So you see this pattern where it kind of goes up and then it comes down, but it never completely goes away. I've also indicated over here a dotted line in red that I'm calling capacity. The capacity is an important measure, important number, and often capacity is sort of thought about at the level of a public healthcare system, and we think about capacity as the number of really sick individuals that we can actually handle in hospitals at any given time. So often that number is based on the number of hospital beds you have and the number of available staff you have and things like that, right? And so you can see that in this particular scenario, the number of infected individuals at its peak was well above capacity, right? And so in real life, if this was the case, this would be a disaster, right? Because you would have immense crowding during this period of time, and you would have all kinds of additional deaths. So in fact, this death rate might actually be a conservative number if you have this actual scenario play out, right? But so this pattern of you have this increase, and then it kind of goes down as you run out of people to infect, and then there's some kind of low level continuing equilibrium rate of infected individuals is the pattern produced by the basic model. Let us see what the real data looks like. So these are caseloads from the first wave. So about 120 days would be about this much. This is from Montreal. This is real data, and you can see that there's a spike. It goes up, it comes down, it never really goes away, right? And so to some extent, we can say that our model has been validated. It does look like that. Now, obviously, our model has a much tighter spike, and that might have to do with some of the other things that we're gonna manipulate here shortly, right? So here you see, under these conditions, at its peak, you had 85 sick people and you had 11% death. Let's see what happens when we start modifying things, right? Now we can say, what if something was different? What if, for example, we convinced 10% of our population to engage in social distancing, right? So that's a reasonable thing. Let's see if we had been successful at that, what would have been the result? Well, you can see that there's been some reduction in the peak, right? It was 85, it's now 82. It's not a huge reduction. The death rate still seems to be unnervingly high, but something has changed, right? There has been a reduction in the peak. So you were talking about flattening the curve. This curve has been flattened. Again, not by very much. So clearly doing 10% social distancing is probably insufficient to really bring this pandemic under control. So what else can we do? What if, for example, we were able to convince 50% of the population to social distance, right? So this is, maybe it's a very strong campaign, and you're really encouraging everyone to do social distancing. We're handing out masks left and right. Let's see what happens. Okay. Now you see the peak has reduced considerably, right? So it was in the 80s, now it is 68. It's still too high. It's still too high, but you can see now that increasing the fraction of social distancing did have a distinct and measurable impact. Let's say we do even better, right? Let's say there's not just a public communication campaign, there are mandates. You can't get ice cream if you're not vaccinated. You can't go into metro if you're not vaccinated. You can't do a bunch of things. And so there really is a lot of pressure, and people have no choice but to get vaccinated. And we achieve 75% social distancing. Sorry, I was talking about social distancing, not vaccinations. I'm sorry. We convinced 75% of the population to get to engage in social distancing through a very aggressive campaign and lots of curfews and things like that, right? So 75% social distancing. We run this this model now, and now this looks a lot more manageable. At its peak, it's only 47. So this is actually, yes, there would be some point in time where there was crowding in the hospitals, but maybe it's not as bad as it could have been, and so this looks more manageable. So certainly, if this was how the first wave played out, that would have been okay. But we know that actually, even in our first wave, at least in Montreal, we were well above capacity, and so that was not good, right? But what else can we do, right? So we know often with these complex systems that there are many levers that we can pull. There are many ways in which we can intervene. So with COVID, of course, we know that vaccination was a very good way to intervene. So let us assume that we are able to convince 1% of our susceptible population to get vaccinated per day, right? So this is a very low percentage, but maybe somewhat realistic. And let's say we can convince nobody who actually has a disease to get vaccinated, right? So what happens when this happens? Let's run the simulation, and now, at its peak, it is under capacity or at capacity, but even that is you're actually talking about the total infected, because the unvaccinated individuals are actually below capacity, and you have some vaccinated infected people. And that's actually good news, because as we know from some of you might remember, the vaccines, in fact all of the vaccines, considerably reduce the severity of the disease, right? So you weren't so bad, and so these people who are vaccinated and infected are not contributing to the crowding issue. So this is actually quite good. Let's say we did even better, right? Let's say we convinced 1% of the people who had recovered from COVID to get the vaccine, and 5% of the susceptibles to get vaccinated every day. So this is really a concerted vaccination campaign. Everyone's firing on all cylinders. We have all the vaccines in place. Civil society comes together. Hope springs eternal. Let's see what that looks like. Okay. And now we see something that looks very much like not a crisis, right? So you do have some spikes in infected people, but for the most part, you are seeing people who are vaccinated and infected. These are generally mild cases of the disease. There's very little hospitalization required in this scenario, and even the deaths are quite low. And so this is very good, right? And so this looks less like a pandemic of great severity and more like flu season, right? Where we have a fairly routinized vaccination process. There are behaviors that people engage in during flu season to stay healthy, and so under these conditions, this is actually not a crisis, right? And so you can imagine a scenario where with COVID we didn't panic, and we sort of had very good discipline in social distancing, and we got the vaccines. At the moment we had the vaccines available, we took the vaccines. That would have been a very different and less horrific COVID pandemic. But anyhow, this is sort of what I wanted to show you, right? So this is the value of simulating. You can sort of explore all these different scenarios. As you can see, there's not a whole lot of complicated math that goes into it. You can play with this model yourself in your own instance of this virtual programming environment. You can use Gemini, maybe even modify, maybe even improve on my model. I would love that. And of course, you could try and do something else. You can adapt this to build a model of some other simulation of some other process model that you built, right? So that's up to you. I do hope that you found this simulation exercise to be useful, and I hope that I slightly demystified simulations for you. Thank you very much for listening.